In this video, I'm actually going to do some practice with interpreting mass spectra. And so I'll actually go through some mass spectra and show how we can obtain some potential fragments from it. And so we'll be using these two tables quite often. So this one right here, which tells us about some of the major alkyl groups that we'll be seeing, and then this table right here, which tells us about some of these main substituents here, like our halogens, our nitrogen, and our sulfur here. And so we'll first look at this one. So I've removed the names from these, but I have actually put in the molecular weight of these just because on some of them we don't see the molecular ion. And so this one does actually show the molecular ion, so we see it right here. So it's at 58, so we go 60, we count down 59, 58 right there. And so we do see the molecular ion on this one. We see our base peak is this one, and this looks like it's at, so we count from 40 to 41 to 3. So this is at 43. So we have M over Z of 43 for our base peak. And then we can look at some of these other larger peaks. So we see we have one right here. This is an M over Z of 29. And so remember, the 43 corresponds to a propyl group. So a propyl group, which is 3 carbons, and a 29 corresponds with an ethyl group. And so we can tell based on this, so we have 58 grams per mole, so that will be something like 4 of our carbons, so 4 times 12, plus if we have if we have just 4 carbons, then we will have 10 hydrogens, right? So 10 times 1, so this right here gives us 48, and then this right here gives us 10, which gives us then 58. And so we can see, because we only have propyl and ethyl groups, we don't have anything larger than that, that we are probably dealing with a butane here. And so we can actually look over here to where I have the answer, and so this is indeed butane. So we see here where we get our 43, our M over Z of 43 at this red one, and our 29 at this green one. And then we will see a 15. That will definitely be a smaller peak, but that is right there. The reason it's smaller is because that is going to be a methyl carbocation, which is going to be less stable than having these secondary carbocations here. So that is our first one there. So we can go down here and try to do a second one. And so the first thing to look for, so we want to see if we have our molecular ion, and it looks like we indeed do have that right here. So we start at 60, and this is another thing to pay attention to is the x-axis on here, because the tick marks aren't always going to be the same. So here looks like we have 60, 65, 70, and this is 71, and that's 72 right there. And so that is our molecular ion right there. And so then this right here must be 55, so this one here is 57, which corresponds to a butyl group. So a butyl group right there. Then we have our base peak right here at 43, so the M over Z of 43. Then we can go 40, 35 to 30 right here, so we have another one at 29. So this, remember, is our propyl peak right here. This is our ethyl peak right here. Then it looks like we have one right here, which is 15, which is our methyl peak right there. And so again, it looks like we have mostly just alkyl groups, and what we see is that the 43 is the major one. And so that means there must be a way of getting a propyl group that is the most stable. And so quite often that means it'll be a propyl group that has the carbocation on the central, on the secondary carbon right there. And so this tells us that one of our fragments is probably this propyl group that looks like this. that we have 57 is telling us that we have fragments that are butyl groups, and so our entire molecule must be something larger than a butane. And in fact, a butyl group, and this is a pretty high peak, so it's likely we have something that looks like this as a fragment. So it looks like we have a more substituted carbon right here. And so what I would propose is putting these two things together, we probably have something that looks like this. So we have a single methyl group, so a 1-methyl butane here, because then we can break it off that way to get this peak here, and we can break it off that way to get this one right here. And it is in fact the 2-methyl butane right here, where if we break off that purple group, it gives us this one in green, and if we break off either of those methyl groups, it gives us this one right here in red. So that gives us our butyl group right there. And so that is how to interpret this one right here. So now we move on to number 3 here. This one looks a little bit more complicated. So it looks like we don't have our molecular ion peak showing up. So we would assume that that would show up somewhere around in this area. And so we don't actually see our molecular ion in this one. So we can go from 80 to 75 to 70 here. So it looks like we have a peak at 71, which corresponds to a pentyl group, so a 5-carbon. We have one at 57, so that is our butyl group. We have one at 43, so that is our propyl group. We have one at 29 here, so that is our ethyl group. This tiny one here at 15 is our methyl group. And so again, it looks like we have mostly just alkyl groups. And so we can maybe think about, so we want to have a stable propyl group and a stable butyl group here. And so it looks like we have a stable butyl group, which is likely going to have the positive ion there rather than on one of the primary carbons, and a stable propyl group, which will look like this. And so that will have it again on the secondary rather than on one of the primary ones. And it looks like we have a fairly stable pentyl group, and so that likely has it on either this one or this one right here. So it has it on one of those two groups right there. Well, we could also, because there are now possible isomers that we can have here, we might have a pentyl group that looks more like this, say. And so that would tell us that maybe it would be on this tertiary carbon. See, this has 1, 2, 3, 4, 5 carbons on it. So it could be a fragment that looks like that instead. And so if we had this right here, and so this looks like it's our largest fragment on here, and so this, if we had this, and so we have our molecular weight of 86, that looks like it's probably the loss of a methyl group. And so likely what we have is something that looks like this as our actual molecule, if this is the loss of a single methyl group, and that's the most stable pentyl fragment. And so what we see is, if we look over here, indeed we do have 2,2-dimethyl butane. And so we can get these 71 peaks by losing any one of those 3 methyls there. We can get the butyl group here by just losing the ethyl group and ending up with everything this direction of that green. We can get our 29, so that is our ethyl group right there. And our 43, so I said we have this propyl group here, our 43. And so what that comes from is we can fragment off this blue one here, so the ethyl group, and then we can still fragment off one of the red ones, because that will give us a relatively stable propyl group with the positive charge on the secondary carbon right there. And so that's what I'm showing in purple here, where we are first breaking off the blue one, and then we can break off one of the red ones and have the carbocation end up right there. And so that is the 2,2-dimethylbutane. So now we can go on to number 4 here. Well, this one has the same molecular weight here, so it's probably some kind of isomer of that, but that might not be a clue that we would start off with. But we do see here that we now have the molecular ion showing up. It looks like our base peak is going to be the 43, so that is the propyl group. And so it looks like our propyl group is one of our most stable forms of this. So we have here a peak at 71. So at 71, where this was 43 right here. So the 71, remember, is a pentyl group. And we have this peak right here, which is at, so we can do 40, 45, 50, 55. So we have one at 55 right there. And so we have one then right here, which looks like it's at about 32. So I would first start just by looking at the 43 and the 71, because those are groups that we are well aware of because they show up in that table. So remember our propyl group, and this is a very stable one, so it's likely going to be on the secondary carbon right there. Then we have the 71, which is our pentyl group, and so that could be something like this. So we might have this, it could be right there, it could be right there. We could also have something like this, where we now have it here. And this looks like a good candidate right here because it's on a tertiary carbon. And so we could also, of course, have it like this. So we have it like that. And so we could have either one, any one of these being our pentyl fragment right here. And so we want to think of how we could get one of these pentyl fragments, given that we are assuming that we would have this as a propyl fragment right here. Well, if we have something like this, then that would let us assume that we have a molecule, and I'm actually going to move over here, that looks like this. And so if we then put one of them right here, so if we're breaking off a methyl group, we get this. We also have two ways that we can get those stable propyl groups if we break it in either one of those directions. And so given that this is a constitutional isomer of the one above, that's the one that I would think that it actually is. And in fact, that is what it actually is. So we can get the propyl groups by breaking it in either one of those directions, and we can get that pentyl group by breaking off one of the methyl groups like that. And so that is going to be 2,3-dimethylbutane. Then we can move on to this one here. Again, I put the molecular weight here. It looks like we do have the molecular ion showing up, but it's very small on here. So what we can then do is look at some of these peaks. So it looks like we are going from 45 to 50 to 55. So this peak right here is 56. And then we can look over here. So we have 45, 44, 43. So it looks like this one is 43, which corresponds to our propyl group, where this 56 looks somewhat similar to a butyl group, which is 57, but it's one less than that. So that might tell us something. We also have this here at 41, and so that is 2 less than our propyl group, and so that might tell us something. And then we have one here at 31. So we have another peak right there at 31. This one here is 29 and 27. So this is always a good thing to do right off the bat, is actually start just labeling what the actual peaks are and seeing if you have anything that looks like what it could possibly be. And so we have here this 56, which, like I said, looks kind of like a butyl group. So that would be something that looks like this. And so we could maybe think of this as maybe having the positive right there, or maybe right there. And maybe we're missing something else on here, which might tell us something as well. And so just as a kind of rule of thumb, things that often take an extra hydrogen away are OH groups and NH2 groups. So these can often leave as water, and these can often leave as ammonia. Well, we know also that one of our little rules is that when we have a nitrogen, we will have a odd M plus with some even fragments. Well, it looks like we have an even M plus, our 74 here, and odd fragments, which tells us that we probably don't have a nitrogen present, and so we can probably rule that out. And so this tells us that we probably have an OH group on here. And so we could have that OH group, maybe it's coming off from right there, or maybe it's coming off from right there. So it's possible that what we have is a butanol, a 1-butanol, or a 2-butanol here. And so we want to be able to determine which of those is the most probable one. And so what we want to do then is look at our fragments here. So again, we have this 43, which is our propyl group. So another type of fragmentation that we can get with these alcohols is we can get something like this with the alcohol right here. And so we can actually get this come off that way, or we can even get it to come off that way. And if we get it to come off this way with the positive charge going that way, then we see what we will have is a fragment with size. So the oxygen is 16, the carbon is 12, and then we have two hydrogens coming off of this carbon right here and this one hydrogen there. So plus 3. We get 16, so 28, 29, 30, 31. So 31. Well, we have a fragment that is indeed 31. And if we have the positive charge instead go that way, then we will get our propyl fragment, which is the 43 here. And this 41 is likely coming from, we get our propyl group here, and then we might have this right here, something like this, and then this can take off one of these hydrogens here, and we can end up with a double bond forming like that. We can have this still be a cation like that. And so we can get a fragment like that for our 41 fragment. And in fact, if we look over here at what it is in fact 1-butanol. So we have this M over Z here, which is 31, where the positive charge goes that way. We have the 41 when it goes this way, and so 1H goes with the OH as H2O, and a double bond is made so that we end up with something like this. Then we have our 56 here, which is just the loss of the H2O. And so those are our fragments on the 1-butanol. So for this one, we again have a molar mass of 74. It does look like a very small peak is showing up there. So the other peaks that we are going to be interested in here, so obviously this big one right here, which goes from 40, 41, 2, 3, 4, 5. So this one is at 45 there. We have this one here at 59, and we also have this one here at 31. So we saw above that for the 1-butanol, which was this right here, that we had a 31 when we broke off right there. So it looks like maybe we have another alcohol group on here. But what we also see here is that we have this one here at 45. And so that 45, if we do 45 minus 31, gives us 14. And so it looks like we have a group that is about 14 possibly breaking off there. What we can probably assume is maybe we have something like this. So similar to the last video, we can have something like this, which gives us our 31. So this right here is 16. Then we have 12 right there. And so that gives us 28. So 28. Then we have the 29, 30 and 31 from the hydrogens, so 31. So we might have something like that. But then we can also have something that is 14 larger than that. And so something that would be 14 larger than that would be something that looks like this. So probably a positive charge right there, where this one had the positive charge right there. And so this tells us that we might actually have a secondary alcohol on here rather than a primary alcohol, where this fragment right here might be coming from breaking off two of the carbons from it. So we start with something that looks like this, and then we break off right there, and then maybe break that one off right there so that we end up with this 31 peak right there. Then the 59 peak would be maybe if we are just breaking off a methyl group from this right here. So we have the 74 minus 59, which gives us our 15 right there. And so that is breaking off a methyl group. And so what I would propose is we have at least a secondary alcohol like that. And it looks like if this is a 74, which is also what we had above, again, it's probably a butane backbone. And so we might have something that looks like this. So we have 1, 2, 3, 4 carbons on here, and so we would get the 59 if we were breaking it off right there, or if we were breaking it off right there. We would also be getting our 45 if we break it off right there. And so in fact, if we look at this, it is what we actually have. So this is the 2-butanol right here. And so we see that we have this 59 right here if we break off this methyl group, this 59 right here if we break off this methyl group, and our 45 if we break it off at this bond right here. And so that is the 2-butanol, which, remember, if we're comparing it to our 1-butanol here, so this one, we get a lot of these same peaks, but we're not getting this 45 peak, or at least not a very large one right there, which is telling us that we probably don't end up with fragments that look like this right here. And so that getting that peak there at 45 is going to be a good indicator that it's a secondary, because this fragment right here is going to have this sort of resonance stabilization where we have our lone pairs here that can go down. We get this, and so we end up with this as our resonance stabilization right there. And so if we go down to our next one here, so we have a M plus of 72 grams per mole. It looks like that one is in fact showing up on here. Then some of these other fragments that we see, so this one, this large one here, our base peak, it looks like it's 59, 58, 57 right there. Looks like we have another large-ish peak right here, which appears to be 39, and we have this one here which looks like it's at 43. So we have 43 right there. Then we have this one which is 29. Well, the 29 is going to look like our ethyl group. So the ethyl group. The 43 looks like a propyl group. The 39 doesn't really fit into any of our known alkyl groups. Looks like we also have a 41 down there. Then this one would be a 27 right there. And so one thing to look at here is that we have these peaks like 41 and 27, which are 2 less than peaks that we often see are alkyl groups. And so those might possibly be alkene groups. So they are minus 2 hydrogens. And so that might be something that perhaps indicates that we have a double bond present in here. We also then see we have the 57 here and the 43, which tells us that we are getting peaks that look a lot like the regular alkyl groups. But one thing that can actually account for that is, so if we have our double bond, which is minus 2 hydrogens, if we have an oxygen, that gives us plus 4 because of the oxygen, which is 16 as opposed to the 12 from carbon. But then it also has 2 fewer hydrogens, and so that would be 2 minus 2H from that compared to just an alkane. And so what we see is that if we take all these things together, the double bond there, the oxygen, then the minus 2 hydrogens from the oxygen, what we get are groups that look just like alkyl groups, and so those would actually have the same mass on their fragments. And so what we might have is something that has an alcohol, so something that has an alcohol like this going off to other things, and we might also have a double bond somewhere on here, so probably something at least that looks like this. So we also have this right here, this 15 group, which tells us that we probably also have a methyl group on here. And so if this alcohol is, say, coming off right there, then the methyl group would have to come off right there if we are going to get to a size of this, because we can't add any more carbons on after that. And so then I would propose that this is 2-butene 1 all. And so it has the double bond in it and it has the oxygen. And in fact, this is what it is right here. So we can get these peaks at 57, we can get this one at 55, this one at 41, and this one at 39. So we look back here, we have our 57, we have our 41 here. Looking at these fragments, our 41 and our 57 right here. The 55 doesn't look like it's that big, so we must not be losing this water on it, but we would see one at perhaps 53 or 54 here if we are losing that water, because that would then take another hydrogen with it. We have our one here at 29, which would look like the ethyl group if we're maybe breaking it right there. And we also see we have our 39 group, which is what I show here in purple. So this would happen if we first did the blue fragmentation, so we break off the water, and then the red fragmentation, so breaking off that methyl group. That could give us the 39 there. Then on our next one here, so the first thing to notice on this, we have this odd M plus right here, which does show up on this, and we have this even fragment, so that tells us that we probably have a nitrogen here. And seeing a even fragment here at 30 with the odd M plus, this is a good indication that we have an amine group that looks like this. So NH2, we have our lone pair there, down to a single carbon like this. So this is a 30M over Z right here. And these are going to show up a lot because they are resonance stabilized. So we can have those go down there and we end up with this right here. So NH2, and then the plus is there, and CH2 right there. So that is going to be our fragment at 30. And if we have other types of amines on here, so if we have a secondary amine, for instance, so if we have something that looks like this is actually going to show up at 44M over Z, as would if we had NH with these coming off of here like that. So this would also show up at 44M over Z. Now, if we have one that looks like this, if we have just 3 methyl groups on here like this, so this will show up at 58M over Z. So those even fragments that look like that when you have an odd M plus are usually good indications that we have an amine group on here. Since we have the 30 M over Z, we probably have the one that looks like this. So it's just on a primary carbon there. And so what we also see is some fragments showing up down here at around 43, and one's showing up down here at around 29. And in fact, what we see is that, especially at this one, we actually see one at 28. And so I said earlier that a lot of times you can get NH3s coming off of here. And so if the nitrogen is pulling a hydrogen off of it, that might lower an ethyl group from 29 down to 28. And so based on this, I would propose that we probably have a butane like this with a primary amine on it. And in fact, if we look over here, that is exactly what we have, where this fragment here in where the red is, that is our M over Z of 30. And so we can get the one here at 41 if we break off that propyl group and then form a double bond, which can happen if our nitrogen takes a hydrogen off of it in a sort of elimination reaction. And so that would be our 41 right there. And so again, this is always a good indication that there's a nitrogen when it's an odd M plus right there, and then we have even fragments. And then you want to look for the even fragment at 30, at 44, or at 58 to try to determine what type of amine that is in it. And so if we go on to the next one here, so now we have one where we have this 137 M plus, and it looks like we have 120, 130, so it does look like we have that showing up. And the other thing to notice on here, we have this. So we have an M plus 2 that is about the same size as our M plus, which tells us that we probably have a bromine in this structure, where the bromine has a 79 and an 81 isotope that are both about 50-50 with each other. And so you will get those same sized peaks where this one will show up 2 after this one. And you can then see these other peaks here. So we have that one, and that one, which are probably alkyl bromide fragments. So alkyl fragments that break off and still have the bromine attached to it. And the other thing to notice here is that we do have an odd M plus, which might make you think we have a nitrogen in here, but if we look at each of these fragments, what we'll find is that each of them are odd. So this one here will be at 57. This one here is at 43. This one here is at 29. And we have the one here at 15, which tells me that this is probably a butane with a bromine bound to it. And in fact, we can see over here that that is what this is. So again, with the bromine, the M plus 2 will be as large as the M plus, and then we get these other alkyl fragments coming off of here. And if we go down to this one, what we see is this is very similar to above. So we have the same molar mass here, and we have this right here. So those two peaks right there are about the same size. We have some of these other peaks right here, and we have the same sized peaks here. So this is the 57, the 43, the 29, and the 15 right here. And so you might think, is this just a repeat of the other one? And a lot of times these can be difficult to distinguish from each other, but what we can possibly do is look at the fact that these alkyl bromide peaks are a lot smaller. And so they're smaller than the ones we have here, which tells us that probably that bromine is coming off an even more stable carbon. And so that tells us that we, instead of a primary carbon that the bromine is on, that it's maybe coming off of a secondary carbon like that. And that is in fact what we have right here. So this is our molecule where we get the 57 peak here, the 29, we can get another 29 here, we can get a 41 here if we lose the bromine and this methyl group right here and form a double bond. And that's how we could get the peak here at 41. And so if we go down to the next one here, what we see is now we have these peaks right here. And we see that we actually don't have an M plus showing up on here because that M plus, well, it's probably hard for you to see, but there is a very tiny red peak right there. It's like maybe just a couple pixels large. But it might be difficult to see, so we might just call this as not having an M plus peak. But what we see here is we have these at what looks like 77 and 79, and the one at 79 is about a third the size of the one at 77. And so that is a good indication that we have a chlorine on here, so a Cl. So remember, the hallmark of a chlorine is that it has a isotope that is 35 and one that is 37, and about 75% of them are the 35 and about 25% of them are the 37. And so we will have a M plus 2 peak that is about a third the size of our M plus peak. But because we can get these alkyl chloride fragments, even if you don't see the M plus peak, you can see those types of peaks in the smaller fragments there, where we maybe just take off a methyl group from it. And what we can see here, so we have a peak at 63, we have one here at 57, and another one here at 56, and we have one here at 41, we have one here at 29. So the 29 is probably an ethyl peak. The 41 is maybe a propyl peak, but we are generating a double bond in it, so we are going to be down to hydrogens. This 63 peak, so something like that, we can just sort of do some trial and error math. So we know that the Cl is going to be around 35, so we'll just do 35. Then we want to do plus, and we can try maybe 2 carbons, so 2 times 12 right there. And so what this will do is bring us to, so 35 plus 24, that will give us 59. And so to get to our 63 peak, we just need to add 4, so probably 4 hydrogens on there. So that would be a fragment that looks like this. So Cl down to a carbon to another carbon. We have a plus there, so this one has 3 hydrogens on it. This one has a single hydrogen on it, so that's probably the fragment that we are seeing there. Then the 57 is probably just going to be our butyl group. The 56 is probably happening if we have our butyl group. So we have our butyl group like this with a plus, and then say this Cl here, which will have the radical on it. We have something like this, so we can then have this go there, that go there, and we lose another hydrogen, and then this becomes something like this with a radical on it. And so this would have a 56 M over Z for that fragment there. So we are losing essentially an HCl from it. And so if we look at what this actually is, it is a 2-chlorobutane. So we can get this 63 here if we retain the Cl and lose an ethyl group. So that gives us this fragment here, which is just what we were looking at before. And so that's kind of the main fragment to see on there. And this one at 41, so we lose Cl and a methyl group, and we form a double bond, probably from that Cl taking a hydrogen along with it. And so if we go down here, so the first thing to notice, so we do have an even M plus right here, and it does appear to be showing up. And the other thing to see is that we have this M plus 1 and M plus 2 peaks right here. And so that is a good indication that we have a sulfur in this, because sulfur has a 32, a 33, and a 34 isotope. And this one is only about 4%, this one is only about 4%, and this one would then be about 92% of the isotope abundance. And so that's why we see these 2 peaks here at M plus 1 and M plus 2. So we have a good indication that there is a sulfur in this. So now let's look at some of these peaks. So it looks like we have 40, 45, 50, so we have 55. So we have one here at 56. We have another one here at 41. And we have another one here at 27. And And so those all look like they are short a hydrogen or two from our usual alkyl peaks. One way that could work is if we are losing an H2S. So if the sulfur takes a hydrogen from it, and we can then also form double bonds. So this again is probably going to be a butyl, and I think you see the pattern here that all of these are butane backbones. And so you could just determine that based on the size of the fragments here. So this 56 being close to our 57 butyl fragment, we don't have any significant fragments after that, so that's a good indication that the butyl is our largest alkyl group. But what we could have is something like this. So if we have a plus on there and we have some hydrogens coming off right here, we can have this with a free radical on it. We then get that and remove one of those hydrogens. And so we can end up with something like this. So some kind of radical cation here. That would be our 56 right here. And we could also break one of these things off right here and end up forming a double bond, and that would give us our 41. Then the 27 would just be doing the same thing with an ethyl group. And so I propose that this is probably going to be 1-butane thiol. And in fact, that is what it ends up being right here. So we have these 4% M plus 2 and M plus 1. We get the 56 here with the loss of an H2S. We get this 27 here where the loss of the SH and an ethyl group and making a double bond, probably from that SH extracting a hydrogen off of it. We can get this 41 from losing the ethyl group and making another double bond right there. And so that's butane thiol. So again, the thing to notice for that is that we have our M plus peak here with the two M plus 1 and M plus 2 that are about 4% the size of it because of the sulfur isotopes. So the next one to look at down here, so we have a 184 molar mass here. It looks like that one is in fact showing up. But the things to really notice on here, the first is that we have this large gap right here, and the second is that we have this peak right here at 127. And so the 127 is a good indication that what we have is an iodine, which has a molar mass of 127. And so if we have the positive ion of that, that gives us the 127 peak. And this gap right here is in fact 127. So this would be our alkyl group with the iodine coming off of it. And so what I would propose then is that we have either something like this, where we have an iodine on it, or it could be something like this. So it's probably not going to be possible to distinguish those two just based on the mass spec, and this is where we would need things like the NMR to actually come in and tell us what is actually going on. And so this is what it is. So it's 1-iodobutane, but we can look over here. So this is the 1-iodobutane spectrum right here. This is the 2-iodobutane spectrum right here. And the thing you could notice is that you really wouldn't be able to distinguish between those two molecules just based on the mass spectrum here. They are pretty much identical. And so if you guessed 1-iodo or 2-iodo on this, if I was grading your homework in like a sophomore level organic chemistry class, I would call either one of those good. But we know just from this 127 gap here and the peak at 127 that we have an iodine here. Then we can use the other peaks to sort of determine what size of alkyl group we have on it. So we have the 57 here, we have the 41 right there, we have the 29 right there. And so those all tell us what kind of alkyl group we have here. And so the last one here, so we have a 122 molar mass. It looks like we do have that showing up on here. So that is our M plus right there. We have this peak right here, which is at 105. So 105 M over Z. We have this one here at 77, and we have this one here at 51. So on here, the first thing I would notice, we have this 77. That is a indication that we might have a benzene ring. So the benzene ring ion is like this. We have our double bonds in it, and we have a positive charge on it. And this has an M over Z of 77. With this 105, which doesn't really correspond to any of the things we have looked at, what we can do is take our molar mass, 122, and subtract 105. And so this gives us 17. And so that is not going to correspond with anything that could have a carbon, like a single carbon on it, because if we have CH3, remember that is an M over Z of 15. So likely this is coming from something that has an oxygen in it. And in fact, if we had an OH group, that would fit the bill right there, because this is 16 plus 1, so we are probably losing an OH group right there. And so what we have is 105. We can do 105 minus 77 to see what kind of group we might still have on here. 28. And so we can try to think of maybe a group that is around 28. So that's close to an ethyl group. So an ethyl group being 29, but it could also possibly be something like a carbon monoxide. So something like this. And that would be a pretty good candidate because that would give us something that looks like this. So we have our C right there, the O right there, and maybe a positive charge right there, which is resonance stabilized by this oxygen. And so if we have this and we're losing an OH group, a good proposed structure would be this right here. So it would be benzoic acid. So OH right there and O. And so the thing then to notice is we have this 51. So this is probably going to look very mysterious to you because there isn't a good place to sort of break this up that'll give us a fragment at 51, at least if you are just thinking of kind of breaking across a bond. But we can also do some sort of fun rearrangements in here. And the one we are actually looking at what's going on here is if we generate this fragment right here, then we can actually do this. So we end up with our M over Z of 77. We do a sort of internal ring radical mechanism. And so we will actually be forming a new bond between those two carbons and another one here between those two carbons, and then we are actually breaking off at this bond and at this bond. And what we are forming is this right here plus this acetylene. And so this is our M over Z of 51 right here. And that is how we can account for that fragment right there. Some of these fragmentations will have strange looking things like that occurring. And another one that you will see quite often is the McLafferty rearrangement. But especially when you start having a lot of these double bonds and double bonds to oxygen and stuff like that, you can start getting these rearrangements occurring inside your fragments. And this is indeed benzoic acid right here. So our M over Z of 105 is coming from breaking off that OH. We do get a 45 here when we do a sort of decarboxylation on here. We can see our 45 is this small peak right here, but it is still a relatively significant peak on there. And so you can actually get decarboxylations coming off of here. So what we would end up with is a fragment that looks like this. So it would look like that. But anyway, that was everything I wanted to talk about in this video, just going through a few problems of these mass spectra and how to interpret them. I hope you found this helpful, and I will see you in the next one.